Okay, so today we're going to be starting section 3.3, which contains the product rules, the quotient rules, and higher order derivatives. So before we start, I want to discuss what the product rule is not. So the product rule concerns when we are taking the derivative of the product of two functions. And it is definitely not just taking the derivatives of the functions independently. And I'll give you an easy example to show this. Let's say our f of x is x squared and our g of x is x cubed. Well, then our f of x multiplied by g of x would just be x to the fifth, and the derivative of x to the fifth, according to the power rule, is just 5x to the fourth. Now, what would happen if I took the derivatives first and then multiplied them? Well, the derivative of x squared would be 2x. And the derivative of g would be 3x squared, and the product of those two derivatives is now 6x cubed. And we can pretty clearly see that 5x to the fourth, which is the answer when I multiplied first and then took the derivative, is not the same as 6x cubed, which is when I took the derivative first and then multiplied the answers. So unfortunately, the product rule is not as easy as, say, the sum rule or some of our other rules. And we're going to come up with the formula for the product rule the same way that we have done all of our others, by doing the limit definition of the derivative. So I'm going to do the limit as h goes to 0. And since this is my new function, I have to evaluate that at x plus h replaced for both of the x values in both f of x and g of x. So think of this as like a new conglomerate function, and the x shows up in two places, so here and here. So I need to replace both of those with x plus h. And then I need to subtract from that f at x multiplied by g of x and divide that whole thing by h. Now at this point, I don't really know where to go with this unless you happen to know what the trick for this proof is. You're not expected to come up with this on your own, but hopefully you can understand once you see it how this trick helps us. So I'm going to employ a technique that will change how this expression looks without actually changing the value of it. I'm going to scoot this minus f of x, g of x off to the side. And in the middle of these two terms, I'm going to subtract something and then add the same thing back in. So I am going to subtract an f of x, g of x plus h, and I am also going to add an f of x, g of x plus h. And this is all still over h. And hopefully you notice that what I've done is I've subtracted and then added something. So that's really adding a 0, which does not change the value of our expression. Okay, so now I'm going to focus on splitting this limit up into two different limits. So I'm going to take these two terms and split them up. And I'm going to take these two terms and split them up. So we'll have two separate limits of two separate fractions. So the first one is this f of x plus h, g of x plus h, minus f of x, g of x plus h, and that's all over h. And then I have a second limit as h goes to 0, and here I have f of x, g of x plus h, minus f of x, g of x, all over h. Now within each of these two limits, there is a common factor. So I have a g of x plus h that shows up here, and I have an f of x that shows up here. So I'm going to go ahead and factor. So I'm taking this g of x plus h out, and then I have f at x plus h minus f of x all over h. And on the second limit, I'm factoring out an f of x, but I can actually take it out in front of the limit because it has no h's in it. Okay, so why the heck did we do that? Well, the reason we did that is these are starting to look an awful lot like derivative definitions. So I have an f of x plus h minus f of x all over h as h goes to 0. And then here I have a similar thing with the g of x. Okay, so with this limit, I can go ahead and replace the h with 0 here. So I'm going to apply this limit to both of these expressions. And when I replace the h with 0 in the g of x plus h, it just becomes g of x. So then I have limit h goes to 0, f of x plus h minus f of x all over h, plus f of x, limit h goes to 0, g of x plus h minus g of x all over h. So I'm not actually going to evaluate these limits. Each one of these limits on their own is a derivative. That boxed out green one is f prime of x, and this boxed out limit one, yellow one, is g prime of x. So if I go ahead and put this all together, I had g of x multiplied by f prime of x plus f of x multiplied by g prime of x. So our final conclusion is if I take the derivative with respect to x of an f of x times a g of x, I'm going to rewrite this just a little bit. I'm going to write the second term first, so f of x, g prime of x, plus g of x times f prime of x. And if we go ahead and take a look right down here at theorem 3.8, the product rule says the product of two differentiable functions f and g is itself differentiable. Moreover, the derivative of f times g is the first function, so f of x, times the derivative of the second, g prime of x, plus the second function, g of x, times the derivative of the first. Now that's one thing I didn't mention in the proof, is that when we started, we kind of had to assume that f of x and g of x were differentiable. Otherwise, these steps that we did right here in the green and the yellow wouldn't have actually worked. So in order to be differentiable, this limit has to exist of each one of these.